morning. Happy Monday. I hope you had a great weekend. Today is a busy day, so just kind of let me remind you here about what's going on. Today at 1:10, we will turn in problem set 2, problem set 3, take-home quiz 2, take-home quiz 3, the organic chemistry lab, the VBMO lab, and exam prep 1. So we're just about through the snow prep, which is good, but still frustrating. Now today we're not going to look at problem set 4. We're just going to take the midterm, which is what the review has been over the last couple of days. That'll be the only thing we do in recitation. After recitation, we will go to lab, and this will be a lab where you will need some safety goggles. And safety goggles are going to be helpful today because of flames. If you don't have some, I can definitely let you share some. But if you have your own, of course, it's better because they're yours and jazz like that. So kind of a crazy day. Questions on any of this stuff? Yeah, Don.
So we're supposed to have the chem lab done? Okay.
At 1:10, that's right. Worst case scenario, you don't have that done, we turn it into tomorrow. That's one. So it's not the other questions? All right, so we're continuing with some review. We started to look at some of these the other day on Friday, but let's go back and check this out. Now this question says, which of the following molecules is likely to have a dipole moment? Now there's different ways to talk about polarity when it comes to chemistry. And polarity is going to be really important when we start talking about solids, liquids, gases, and the differences between them. So what this question really is saying is that if a molecule has a dipole moment, that means that it's polar. So it basically is saying which of the following molecules is polar. So see if you can figure out which one of those on there is a polar molecule, and we'll go from there. Okay, so let's review here a little bit how to do Lewis structures. And we'll start here with NF3. Now again, Lewis structures are the backbone of basically this whole section. So again, to do something like NF3, count the valence electrons. Nitrogen's in group 5, so there's 5 valence. Fluorine is group 7, so 7 valence, and there's 3 of them. Excuse me. That's 26 valence electrons, and if you divide by 2, that would be 13 pairs. The central atom, usually the first atom listed, it's never fluorine. Oxygen doesn't like to be in the middle, usually either. Lowest electronegativity goes in the middle. So fluorine definitely goes on the outside. We'll connect the fluorines to the nitrogen with lone pairs. That's 3 of lone pairs, so I've got 10 left. Give the outer atoms the octet. If there's anything left over, put it in the middle. So if you fill up the fluorines with lone pairs, that's 9. There's 1 more left. This would be nitrogen there has a pair. If you're going to extend the Vesper geometry, you would think about the number of clouds around the atoms. Clouds can be lone pairs. They can be single bonds, double bonds, or triple bonds. And so this molecule has 4 clouds around it. 4 clouds, even though it doesn't ask for it, would be tetrahedral for electron pair geometry, trigonal bipyramid. Thanks for playing. Trigonal pyramid, Come on, caffeine, start working. Trigonal pyramid would be the molecular geometry, 109-ish angles. Any questions on that? Okay. Now, beryllium difluoride is another molecule on there. Now, most of the time, the central atom wants to have an octet, but there are some that can go under. So beryllium is actually an element in group 2. Fluorine is 7, and there's 2 of them. So 14 plus 2, 16, that would be 8 pairs. So when beryllium is definitely going to go in the middle, it's arguably more metallic. Connect them on the outside, 1, 2, 3, 4, 5, 6, 7, 8. This would be the Lewis structure for beryllium difluoride, or beryllium fluoride if it was ionic. This beryllium has 2 clouds around it, a fluorine on each side. So this would be linear. Why would it be good to make a double bond fluorine with one of the berylliums? And we could do it on both sides, but what would be one reason why that might be good? Especially if we did this. Gives it an octet and stuff, would fill it in, stuff like that. You bet, absolutely. So it might be tempting to do this kind of thing. But the reason why fluorine is always going to have just single bonds is due to formal charge. Now, formal charge of an atom, let's look at this fluorine right here. Formal charge is group number 7. You subtract all of the lone pair electrons, which would be 6, and you subtract the number of bonds. So when fluorine has a single bond, your formal charge goes to 0. Now when fluorine has a double bond, group number is 7. This double bond has 4 lone pair electrons and 2 bonds. This would make the fluorine a positive one. So if we were to draw double bonded fluorine, both fluorines would become positive 1 and beryllium would become negative 2 when you figure out its formal charges. Why is fluorine positive and beryllium negative? Probably not going to fly. The more zeros, the better. I love that answer. That's a really good answer. You bet. So one reason why this is not as cool is if you make single bonds here, all of your positives and negatives go to 0, all right? So it is better overall to have single bonds with fluorine. Another really good reason is electronegativity. Electronegativity is how much an atom is into electrons. And of all the elements on the periodic table, fluorine is more into electrons than anything else. And it being positive, while beryllium, almost a metalloid, is going to be negative, definitely is not going to fly. So I don't say this very often, but if you have a Lewis structure with fluorine, it's going to always be single bonds, no double bond fluorines, all right? So that's one thing that might help and stuff while you go through any of this. Anyway, questions on that? Okay, so this question is all about something's going to have a dipole moment, which means it's going to be polar. Now, to figure out if something is polar, you again look at the central atom. And if everything around the central atom is the same, then it's going to be nonpolar. However, if there's even one thing different around that central atom, then it's going to be polar. So around the beryllium, for example, there's a fluorine to the right and a fluorine to the left. Beryllium, by the way, is one of the weird ones that can have less than an octet, so this is legit. But what it also means, these fluorines are going to be 180 degrees, and they're both pulling electrons towards it, but they pull in equal but opposite directions. So beryllium difluoride would be nonpolar. It will not have a dipole moment. There won't be anything to measure because those fluorines should cancel it out. On the other hand, the nitrogen up here in NF3 has 3 fluorines and a lone pair. So you're breaking the symmetry around the central atom. So the NF3 molecule is polar, All right, that lone pair is going to make it enough different that it's going to have a little bit of a different effect. So if we were going to put both of those chemicals in the dipole measurement machine, which does exist, we would actually measure something with NF3, beat EF2, would just kind of sit there. So long story short then, the one that should have a dipole moment will be NF3. NF3 has a lone pair on it that breaks the symmetry around the central atom. So here's beryllium difluoride. You can see it's got nothing but Fs, just like SF6 has nothing but Fs, C has nothing but H's, stuff like that. The elements by themselves are considered to be nonpolar, all right? They might be paramagnetic or something like that, but they are nonpolar because they're just individual atoms. Questions on that? All right. So here's a question that says, which hybrid orbital set is used by the boron atom in the Bcl4-1 ion? Now, hybrid orbital set is the same as hybridization. So if you see some answer like that, hybrid orbital set and hybridization will be the same. So you can see what your answers are there, SP, SP2, SP3, etc. What I would do is try to see what the electron pair geometry is around the boron, and from there you can find the hybrid orbital set or hybridization. So see if you can do that, we'll talk about it a little bit. Excellent. All right. So like before, Lewis structure, boron is in group 3, chlorine is in group 7, and there's 4 of them. And again, if you have a minus charge, it means you add electrons, and positive means take away. So we're going to add 1 to this thing. We've got 28 plus 4, 32 electrons, which would be 16 pairs. Boron goes in the middle, Cl goes around the outside, connect the outer to the inner, give the outer atoms lone pairs, give them the octet, and sure enough, the Bcl4-1 ion looks like that. So it's boron in the middle of a tetrahedral thing. And like people seem to have a good concept for, things that are tetrahedral are always going to be sp3. So you look for the electron pair geometry. So electron pair geometry will tell you a couple of things. It'll tell you the hybrid orbital set or hybridization. It'll tell you the bond angles around it. So it's cool for chemists. Questions? Good. All right. This is a question with a couple little hidden things I want to talk about. Cysteine is one of the amino acids that are used a lot in our bodies, and there's the structure. And what I'd like you to do is tell me how many sigma and how many pi bonds there are in the molecule. So see what you can figure out here, and we'll talk about what it means to have a sigma or a pi bond. There's one double bond there, and we'll talk about that. Cool. All right. The first bond you draw between atoms in a Lewis structure is always going to be a sigma bond. And so there's a lot of sigma bonds on here. Like that's a sigma bond, that's a sigma bond, stuff like that. Why this question is important is I want to talk a little bit more about what a double bond is. All right. Now a double bond is two bonds. All right. And I've already used Donovan's hands enough, but the first hand, Donovan, good to see you. That's the sigma bond, all right? But when we make a double bond, the second bond that comes in is a pi bond. Yeah. So if you see a double bond, that represents a sigma plus a pi bond. Double bond means two bonds. So this right here is both one pi and one sigma, all right? So if you know that little detail, then 1, 2, 3 sigmas, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sigma bonds. And this thing up here, this double bond, has also one pi. So there would be 13 sigmas and one pi. Yeah.
And then like a triple bond, just to follow up, would be 1 sigma and 2 pi.
Yes, well done, David. You took the words right out of my mouth. That's right. So if you have to count sigma bonds, just remember that a double bond is both a sigma and a pi, and like David said, a triple bond would be 1 sigma and 2 pi. All right. So a pi bond and a double bond are not the same; they're different. So. Questions on that? Another thing that's really important about these is you can figure out the bond angles. And again, you'll just use electron pair geometries to figure it out. So on this particular molecule, cysteine, see if you can figure out what those three angles represent. So what I would do around the central atom in the angle, find out what the EPG is, and then apply the appropriate geometry and stuff to see what's happening. So. All right, chemists have never been artists, that's definite. So in a molecule, when you're drawing a Lewis structure, remember that Lewis structures don't have anything to do with the actual geometries. So with this structure that was drawn, if you just looked at the molecule itself and didn't think about the geometries, the HSC, that's straight across, so that looks like 180. And the OCO right there looks like a 90 degrees as written. And the HNH also looks like 90. So it might be tempting to put answer D down. But remember, those are all artificial. All right, you really need to analyze what that central atom is to figure out what the geometries are. So around this sulfur, for example, we have 2 lone pairs and 2 clouds, 4 clouds total. What is the electron pair geometry when you have 4 clouds around something? Tetrahedral. Yeah, tetrahedral. And when you have tetrahedrons, the angles are going to be 109. So it's not 180. It looks like it's 180. I totally dig it. But in the real world, where people actually have to worry about the angles and stuff, that's more like a 109, like a bent thing. Now over here, this carbon has a double and two singles. This is a trigonal planar electron pair geometry. Remember that the double bond and a triple bond counts as just one cloud. So 1, 2, 3 clouds would be trigonal planar. That's going to be 120 degrees. And finally down here with this nitrogen has 1, 2, 3 single bonds to atoms and a lone pair. That's another 4 cloud system, 109 degrees. So the best answer here would be B. You've got a tetrahedron, a trigonal planar, and another tetrahedron or tetrahedral. So the first and the third ones are 109, and the middle one is 120. Again, the drawings will make it look like you got 180s, 90s, 90s, and stuff like that. But in the real world, the electron pair geometry, yeah. Questions on that? Okay. Now, nitrogen can lose an electron to go from N2 to N2 plus. And the question is, what is the bond order then of N2 plus? Now, the ultimate way to do this would be to draw a Lewis molecular orbital diagram. And you can think about what the MO would be for neutral NO, and then take away an electron to make N2 plus. But you might be able to do this through a Lewis structure. Anyway, by hook or by crook, see if you can figure out what the bond order should be. Okay, so molecular orbital diagrams. On the left and the right, you have the individual atoms, and in the middle, you have the molecular orbital part itself. So here we've got nitrogen on the left, nitrogen on the right because it's N2. And I would start with the neutral version and do the ions from there. So nitrogen has 7 electrons. If you do the full MO diagram, that would be 1s2, 2s2, 2p3. Each electron goes in its own house because of the rule, blah, blah, blah. But on the right, you're going to do the exact same thing, 1s2, 2s2, 2p3. And then the MOs themselves in the middle, like the 2 atomic 1s make 2 molecular orbitals. The lower one is sigma 1s, the upper one is sigma star 1s. This is anti-bonding, this is bonding. And same thing for 2s, sigma 2s, sigma star 2s. For this part, you need to decide if you have an NBC or an OFNE diagram. This is definitely NBC because N2 has 2 N's in it. So we're going to use the 2, 1, 2, 1. And this is pretty sloppy, but your diagrams in your book will do better. Pi 2p, there's 2 of them, sigma 2p, pi star 2p, sigma star 2p. So when you have 3 and 3, 6 electrons, you start with the lowest ones and just work your way up. So 1, 2 filled in first, 3, 4, 5, 6. This would be the MO diagram for N2. Questions getting to that part? Cool. Now, for NO, or thankfully, N2, the overall bond order, 1/2 bonding electrons minus anti-bonding electrons. So it's the ones without a star, the bonding, 2, 4, 6, 8, 10, if you do the whole thing. And we'll subtract from it all the ones with a star, the anti-bonding. So 2, 4, and these are all empty, so 0. So neutral N2 has a bond order of 3. And that's kind of cool. And this corresponds with the Lewis structure for N2. If you were to draw it out, it would be just a triple bond. Each lone pair has a lone pair. Nitrogen has a lone pair. Now, one of the things, though, where MO is really cool is on a problem like this. N2 plus, if we had to redo a Lewis structure, we'd have to rethink about Lewis valence electrons, blah, blah, blah. But N2 plus for MO just means take away 1 from the highest occupied molecular orbital, the HOMO. That would be the sigma 2p here. Notice that we're taking away a bonding electron. And once you do that, kabam, that's the MO diagram for N2 plus, which is really pretty cool. Now, down here, the bond order for N2, it was 1/2 10 minus 4, but we took away a bonding electron. Excuse me. So 1/2 9 minus 4, 1/2 of 5, you have 2.5 or 5.2, something like that. 5/2, something. So yeah, so that's how you can very quickly find the bond order, which is really cool. Now, drawing the 1s all the time is a little tedious, especially when you get to the bigger ones. So you can write core or core electrons there in square brackets. That's a nice way to save yourself some time. Core or core electrons are fine. Any questions on any of this? Yeah.
Can we shorthand it, like do like the parentheses 1s? Right.
Yeah. This is an example of doing the shorthand. The shorthand would just be, the core would be sigma 1s and sigma star 1s, Donovan. And then after that, this would be sigma 2s, and there's 2 electrons in there. Sigma star 2s, 2, etc. But you bet you can use that. You bet. Other questions? This is cool. All right. It asks about N2 plus being diamagnetic or paramagnetic. All right. If you go back to the structure, when an up arrow has a down arrow, those 2 electrons are spin cancels. So this interaction right here would be a diamagnetic interaction. But for the whole molecule, if even 1 electron is unpaired, it's going to be paramagnetic. So N2 is plus is definitely paramagnetic. Now N2 neutral had an electron right there, so it would be diamagnetic. that would be a different kind of thing. But again, you can quickly tell what's going on. So. Questions? Good. So here's another example of a molecular orbital question. The superoxide ion is O2 minus 1. And see if you can figure out the bond order for that one. The O2, the molecular orbital diagram will be similar to this, but this will be the other kind, the phone, F-O-N-E, and that's a 1, 2, 2, 1. So see if you can figure it out. I'm gonna repurpose this molecular orbital diagram right here a little bit. We'll make this work. Okay, so like with the N2 plus thing we saw earlier, with this one what I would do is start with neutral O2, and then we can add an electron in to do a pretty chill. So up here on the blackboard, I have neutral O2. Now, a couple of things that are different, because O has an FO or NE, we need to use the 1, 2, 2, 1 molecular orbital diagram. The top part is the same, it's the bottom part that flips. So in the NBC, the pi's were lower than the sigma 2p, but in the FONE, it's reversed. And that can make a little bit of a difference on things, so just FYI. So oxygen is 1s2, 2s2, 2p4. So you can see I have 2p4 now on both sides instead of just 2p3. So these fill up just like before, and up here, we now have 8 electrons for neutral O2. So 1, 2, and sigma 2p, 3, 4, 5, 6 fills up pi 2p. But most importantly then, 7, 8, remember Hund's rule says put an electron in each side, so this will be a paramagnetic molecule. You don't want to have this electron in this orbital because they're the same energy, blah, blah, blah. So O2 bond order, 1/2 bonding minus anti-bonding. You can include these or not. Down here, I did not include them. All right, I just included the top part where most of the action is. So if you look at just the top part now, 2, 4, 6 minus 2, half of that bond order comes out to be 2. Questions on that part? Okay. This part though is really not about O2, it's about O2 minus 1. And so what we want to do then is just put an extra electron in. Now, the exciting part is in the molecular orbital diagram. And on either of these pi stars, you can put that extra electron. Now you can put it on one side or the other over here if you'd like to. It's not really critical. It doesn't matter if you put it on the left or the right. So it's not required that you put the extra electron in one of those, but you can if you want to, okay? The important part is here in the middle. So what we did just now is we added an anti-bonding electron. So down here, instead of 1/2 parentheses 6 minus 2, now we're gonna have 1/2 6 minus 3. And our bond order, which was 2 before, is now gonna go down to 1.5. So O2 minus 1 should have a bond order which is 1.5 instead of O2, which was 2. Here's the shorthand notation like Donovan was asking about too. Any questions? Sweet. Before we go into alkanes and stuff like that, I did want to say that on these things, remember two things about MO diagrams. Always bond order equals sigma plus pi, and that applies to Lewis structures as well. So in this one, you could do like 1 sigma bond, and as it turns out, half of a pi bond, and 1 plus 0.5 is 1.5. That applies to Lewis structures as well. Sigma plus pi equals overall bond order. And the other thing about bond order is that as bond order goes up, your bond length goes down. So the single bonds are longer, the triple bonds are shortest. It's an opposite relationship. Questions on that kind of stuff? Okay, then knowing this, now let's shift gears and talk a little bit about the OChem. Now OChem is going to be the smaller part of this midterm, but there are going to be some questions on it. On this one, I'm going to kind of just go through the questions like a tutorial. You're welcome to do iClicker stuff if you want to, but I'm just going to talk about it. When you have an alkane, every carbon has single bonds to either other carbons or hydrogens. And so this has a total of 9 carbons in it. So if there's 9 carbons, it would be technically a nonane, because nonane is 9 alkane, 9 carbons. But what you can probably see here is that there's something else going on. So as we talked about in lecture, in organic chemistry, longest chain, smallest number is always the way to go, all right? Longest chain and smallest number. Now to figure out the chain of carbons, it's like putting your pencil down and trying to circle through as many carbons as you can. So like I could do 1, 2, 3, and that's okay. I could go right to left, 1, 2, 3, 4, 5, 6, and that's not bad. But of course, you can probably see you can do even better if you start here and go down through this part of the carbons. So 1, 2, 3, 4, 5, 6, 7. So I get most carbons in my chain when I do this kind of thing. So this compound, because of the longest chain, is going to be a heptane. All right, hept is 7, thank you, and heptane is the longest one. It's not going to be a hexane because hexane is only 6, heptane is 7, and that's coolest. Now after that, in my carbon chains, my 7 there, I need to have the smallest number. And why that's important here is that in these 7, there's a CH3 right there that's not part of my chain, and there's a CH3 right there that's not part of my chain. So this is going to be some kind of dimethylheptane, all right? Because those 2 methyl groups, CH3, aren't there. So smallest chain, longest chain, smallest number. You should, when you're learning, count both directions. So I would go 1, 2, 3, that's one of the methyl groups, 4, 5, 6, 7. So you could call this a 3,6 dimethylheptane. But like I said, count both directions. If you start on this side, 1, 2, 3, 4, 5, 6, 7. Notice that the 2 and the 5, if you count this way, are both dimethyls. 2, 5 is smaller numbers than 3, 6. So this one is best called 2, 5 dimethylheptane. The longest chain of carbon atoms is 7. There are 2 methyls not part of it. If you count from, notice I give this methyl instead of that one, that's fine. 7 methyls this way, then you have a 2,5. Lucas, you had a question.
Yeah, I'm just having trouble with like hexane and how when you remove like the hydrogen that's put on a ethyl at a certain spot, that you have to like move the hydrogen or something, but I don't know where to.
When it all comes down to it, all the things from the Lewis structure still apply. So your carbon's only going to be having 4 bonds and stuff. If you're taking off hydrogens and adding carbons, I think then you're going to have it'll be more than a hexane probably. It'll be a dimethyl or a heptane or something like that and stuff. But just keep all the things you've learned about Lucas on the Lewis structures in the back of your mind, because they all still apply, all right? It's a weird packaging we get in organic chemistry. The red here is my longest chain, and again, that you just want to try and circle or put your pen down, whatever, through the longest number of carbons. And it looks like you should be able to call it a hexane if you go left to right, right to left. But a lot of times in organic chemistry with these branch parts, then you got to start thinking about other possibilities. So you do get more carbons if you include the ethyl group in this chain. It's no longer a hexane. Heptane is longer. Any questions on that? Now, here's a compound. And the question is basically, what's the name? What's an isomer of what? Blah, blah, blah. All right. When it says it's an isomer of something, that's when you count up the total number of carbons in C. So if you count up all the carbons in here, there's 1, 2, 3, 4, 5, 6. If 6 carbons were a thing, you'd have a hexane if it was right in a row, like N-hexane. So we would call this an isomer of hexane, all right, because there are a total of 6 carbons. Isomers of octane would have a total of 8 carbons, pentane would have a total of 5, blah, blah, blah. So if this is a hexane, then it's going to be one of these. And you can see here what the differences are. Dimethyl's in front of them, but there's 2, 2, and 3, 3. Well, this is that smallest number thing. And again, count both ways. So if you count left to right, 1, 2, 3, 4, it looks like the dimethyls would be off the 3rd carbon, so 3, 3 dimethyl. But if you count right to left, 1, 2, 3, 4, 2, 2 dimethyl is another good name. And in organic chemistry, longest chain, smallest number is the winner. So 2, 2 dimethyl butane would be the official name of this beast. Any questions on that? Now, there's some formulas that tell you what the different compounds are. And this can be kind of handy, because some of you will work on some compounds that I have no idea what they are. But if the formula is CnH2n plus 2, then I will know it's an alkane. Now what that means is that for every n carbons, if you have 2n plus 2 hydrogens, then you're going to have an alkane. So for example, let's look at number 4 first, all right? Well, n would be 7. So 2n plus 2, 2 times 7 plus 2, you'd have to have 16 hydrogens there for that to be an alkane. So that is not an alkane. Don't know right now what it is. Well, I actually do, but anyway, you don't have to know what it is. It doesn't follow the formula, all right? And that's the important part. And if you look like right here, for every n3 carbons, you don't have 2n plus 2, 2 times 3 plus 2, 8 hydrogens. So that's not an alkane. This one, same thing. However, this one right here, if n is 11, then 2 times 11 is 22 plus 2. Sure enough, C11H24 is probably going to be an alkane. It's the only family that I know of that follows that structure. So this is kind of a cool thing. So one day, Lucas is working on some kind of cool fuels, and he says, hey, I've got this C11H24 compound, and he'll tell me all about it, and I'm trying to think, okay, what kind of a compound is it? CnH2n plus 2. He's working on some kind of an alkane. I won't know more about it. I don't know if it's a, dimethyl nonane or something, but at least I'll know it's an alkane. secret tricks of chemistry instructors 101. All right, some of the compounds don't have just carbon and hydrogen. Some of them have oxygen. This is an example of an alcohol. All right, alcohols are known for a couple of things. First of all, they'll have literally an OH on the formula somewhere. All right, but you can also tell it from the name. Alcohols have OL endings on them. So because I see this as an alcohol, I know the answer is going to be C or D. OL and alcohols go together. So if you have an OH on the compound, it's not carboxylic acid, something like that. It's gotta be an alcohol. It's gonna have an OL in it. So this compound has 4 carbons. It would be butane if it was an alkane, but because it's an alcohol, we'll call it a butanol. And because you could have the OH on this carbon or even this carbon, there's going to be the numbering thing going on. Now left to right would be 1, 2, 3. That's not even an option because right to left gives you 2. So we have to give that alcohol a number. It's not just like butanol because there's a choice of where the OH goes. So you could call this compound 2-butanol, or the better, fancier name, butan-2-ol. All right? But again, you have to have an OH to give it an alcohol name, all right? And if you have the OL, then you know there's going to be an OH in it. Yeah?
If we had it on the first carbon, would we say butan-1-ol?
Yes,
Yeah.
perfect. That's right. That's exactly it. Nice job. I would let 1-butanol slide too, but butan-1-ol would be the cooler name. Yeah, good. Good call. All right. Now, ketones, aldehydes, and carboxylic acids have what's called a carbonyl, which is a C double bond O. And that's a whole different reactivity thing and stuff that's possible. And that's why I wanted to bring this question in. Now, if you have a C double bond O like this one, and there's an OH next to it, it'll be a carboxylic acid. That would be like butanoic acid. But there's no OH next to this one, so it's not a butanoic acid. We just saw that the OL is an alcohol. There's no COH bonds on here, so it's not an alcohol. And an amine is a nitrogen-containing organic chemistry thing. No nitrogen, so it's not going to be 2-butylamine. So this compound, like I said, then the remaining pieces will either be an alcohol, thanks for playing, aldehyde, which has an AL ending, or a ketone, which has an ONE ending. So we need to figure out here if this is a ketone or an aldehyde. And I don't care how you do it, but a C double bond O with an H next to it is an aldehyde. So if this was a C double bond O and there was an H right there, then it could be maybe butanal, an aldehyde. But if the carbonyl has carbons on both sides of that carbonyl, like this one does, then it's a ketone. And so it'll have an ONE ending like that. So 1, 2, 3, 4 carbons where the C double bond O is in the middle. This compound would be butanol. So butanal would have a C double bond O right there, and this would be just CH2. Butanoic acid would have a C double bond O on the end with an OH, that OH next to the C double bond O. But this is a ketone, C double bond O is in the middle. This one in the next example, this is a carboxylic acid. There's 5 carbons, so it would be pentanoic acid. This would be an example of one of the other kinds. If this was just an H right there, it would be pentanal, an aldehyde. Organic chemistry and stuff like that. It gets kind of crazy. All right, that's really it and stuff for OChem. We're going to start the gases on Monday. Back to good old, normal, in my opinion, kind of chemistry. So I'm kind of looking forward to seeing it. Cool, we'll take care of business. All right, have a great day. I'll see you today at Monday at 1:10 p.m. and 25 minutes.